So good morning and welcome to the private AI session. Let me tell you in advance, it's going to be the best session ever.
It's a private information.
Yeah, it's private information, so the rest of the sessions don't know that. But so today we're going to talk about privacy and security in AI. And the reason for that is that as AI matures and we see it being applied in more and more places, suddenly issues of privacy and security become a concern. For example, when you work in the health domain, even in order to get the data that you might want, you actually need to reassure different health centers that they can share the data with you. And that might be a challenge, both because they might have legal concerns or even competitive concerns preventing them from sharing the data. So today we're going to hear about different aspects of these the related problems, ranging from cryptography techniques that are being used to provide privacy in these settings, to the kind of machine learning techniques that we want to use to solve these kind of problems, as well as see different applications and different domains in which these needs arise. Our first speaker is Christine Lauder. Christine is a mathematician, cryptographer, research group manager, member of the leadership team of MSR Redmond, and is a former president of the Association for Women in Mathematics. And today she's going to talk about private AI and how we bring together cryptography and machine learning to solve different applications, different tasks.
Okay. Thank you, Ronnie. So can everyone hear me? So thank you very much for coming. It's great to see such a broad audience here. It's a privilege to get to participate in this faculty summit focused on AI. We're very pleased with our kind of agenda of private AI, which we'll tell you about today. And at the high level, the thing that you can take away, that you can remember from this session is that from our point of view, this is kind of an exciting new research area, which is a combination of kind of machine learning research and cryptography research. So that's, I think, one of the most exciting things about it is to make progress in this area. We're fundamentally combining kind of new cryptography with new ML in some sense. And so I'm very pleased to be participating in this session with both Ran Gilad-Bachrach, who's a machine learning researcher, and Rich Caruana, also machine learning researcher, and Jung-Hee Chian, who's a cryptography researcher. So you're really seeing kind of both sides of the picture, and we'll show you some demos that show you kind of live, how in action, how this works to bring the machine learning research and the cryptography research together. Okay, clicker is working. So this is our cryptography research group at MSR. I show this because I'm going to talk about a range of projects that fit into our private AI agenda. And these projects are all collaborations with some subset of our group. And in particular, the slides and demos I'm going to show, I want to thank Kim, Lina, and Ronnie for their help with these slides and demos. So there's a distance limit on using the clicker. So the idea is that we can make advances in kind of big data and predictions using data that we collect from people and patients and consumers and things like that. But the question is, you think of it as kind of a trail of breadcrumbs that we're creating a story or predictions or predictive models from. Are we at risk of losing our privacy in this process, and will people want to share their data? So those are kind of some of the fundamental questions that we're concerned about. And give up on the clicker. So using advanced crypto techniques, there's a number of things we can do. So the kind of three crypto techniques that I'd like to talk to you about today are homomorphic encryption, secure multi-party computation, and differential privacy. So just to kind of get an idea of the audience, could you just raise your hand if you're familiar with these concepts? these. So we've got some cryptographers and quite a few other people from other domains. So I'll talk a little bit about what these things are and how we can use them to create private AI tools to improve our ability to provide services on people's data. Okay, so we're trying to apply privacy to the entire process. So what does that really consist of? So think about the first stage, which is really training models based on data. So when you're doing that, the training data is being exposed to the entity who's building the model, for example, a cloud provider. And the next stage, a very fundamental stage where potentially even more kind of consumers and more people's data might interact with the model, is the prediction stage. So if a model has been trained and now you want to give your, for example, your private genomic data so that you can get a prediction on your data from this valuable model. So think about, you might want some prediction of whether you have mutations that are likely to lead you to having some known disease, then that process exposes your private data, your private genomic data, to whomever is making the prediction. There's also the possibility that over time, especially in kind of a malicious adversary setting, if you had somebody that was, successively querying a model many, many times, you could also end up leaking data from just from using the model, leaking data about the training data. So that's another kind of risk. And then a third kind of scenario is another kind of basically statistics, which is not exactly, I'm not exactly sure if you would call it AI, but it's certainly very common, that there could be a large amount of data that's being aggregated, and you want to have the ability to answer people's queries about this data. How many people in this state had a certain, property that, or, had a certain characteristic that you'd like to know about. So aggregating data and answering queries about it also fundamentally potentially can leak information that can invade people's privacy. So I guess one thing I should say before I go on is that I'm not a privacy researcher in the sense of kind of defining privacy, and this talk is not about necessarily defining privacy, but that is a huge part of the discussion. So as we go forward with AI and our fast evolving world, I think we're going to continue to need to have this discussion about what is privacy, what are the requirements, and there's a lot of great work that's been done. I've gone to many privacy conferences and people that think about this notion. Does it mean that when you for example, you get your genome sequenced, that you have to explicitly consent to every single way that it's going to be used? Can there be a notion of people having their data being used for one thing, and not for another? Is there some kind of trade-off between the societal good when the data can be used to basically build, for example, powerful models for predicting, health and well-being that can then be used to benefit other people, including some other people in specific patient populations. So there's some notion of societal good between the trade-off of you sacrificing some of your privacy weighed against the societal good from using that information. So there are all these kind of nuanced ethical questions. And so in my segment here, I'm putting a lot of that aside. I'm just trying to say we do have technology. We have some technological solutions that can be used to help solve this problem. They can be used as at least partial building blocks in these different areas to put safeguards in place before we go too much forward, zooming into the future with just making everybody's data available to everyone all the time. So that's kind of my disclaimer on we're not solving all privacy problems, and I'm not even precisely defining it, but these are important building blocks that I think that society should be aware of. So the main thing I'm going to talk about first, and if I have a little more time, I'll talk about the first and the third scenarios. But I'm going to focus on this second scenario because it's something that we can enable pretty well today, and so it's kind of an interesting use case for our technologies. So Here you should think, I mentioned already the idea of prediction. So you get you have your genome sequence and you have your genomic data that you're storing on your laptop or something, and then you find out about a new service where some medical researchers have figured out a model to predict whether you have some particular disease or not, and you would like to get that prediction, but without sharing your genomic data with that service or that hospital or whoever has created it. So that's one scenario, but there's also, you can think of it also in terms of kind of an enterprise scenario. So there could be a bigger entity such as a hospital or a cancer research institute or a large company. They could have their data stored in the cloud, and they could have built some models that are useful to them in their business, let's say. And they might want to make these models available for others to get predictions, maybe other partner companies or maybe other patients or things like that. So this model of prediction is very flexible. There's a lot of possibilities as to whether the model needs to remain private or not, and who can get predictions and these kinds of things. So I'm going to focus on that, and if we have a little time, we'll go to the first and third scenarios. So in the second scenario, the main technology that we're talking about here is called homomorphic encryption. So homomorphic encryption is just a kind of a fancy math word for a fairly elementary idea. What it means is it's a way to encrypt data. So encrypting data just kind of transforms it into this kind of secret way, this secret package that you can only undo if you have the key. So encryption is intended to preserve confidentiality. But it's encryption that actually can be done in, you can reverse the order of encryption and computation. So what that means is that you can either, you have several pieces of data, let's say, lots of different information about a patient, and you're going to do some kind of statistical computation on this data, and you're going to first encrypt the pieces of data, and then you're going to operate on it, and that will give you the same answer as if you had first just done that computation locally and then encrypted it. So that's all that homomorphic encryption means. So I have kind of two different ways to describe homomorphic encryption with pictures. So this is kind of a typical mathematical way of describing things, which is like a commutative diagram, which basically says that you have two pieces of information that are private, A and B, and you can either compute on that information, which is that top arrow up there, and you get some output, for example, A plus B, or you could encrypt that information, so you could do either one of these first. And what this commutative diagram is saying is that if you do this, if you follow these arrows in either order, you'll get the same thing. You'll get an encryption that will decrypt to the same output, which is A plus B. And the homomorphic encryption that we want to consider here has the property that you can actually compute any circuit on the data. So you can do both addition and multiplication, which corresponds to and OR gates. So this is a very powerful tool because it means that you can kind of compute on encrypted data. And you might say, okay, well, why do you want to do that? So here's another description of homomorphic encryption that's usually a lot more popular due to the picture of Homer Simpson. So I like to call this homomorphic encryption. So I can't take credit for that joke. That was actually tweeted live during one of my talks that we were talking about homomorphic encryption, so it was not my idea. But anyway, so the idea is that Homer Simpson over here, looking somewhat puzzled, is our jeweler. Suppose you had some gold and you wanted to have some jewelry made from your gold. So that's an analog of doing computation. So there's some resource which is valuable, the gold, and then there's some task to do. So it's analogous to having some data, and you need to perform some computation. Here it's some gold, and you need to, make some jewelry. So, but you don't necessarily want to trust your jeweler to just kind of hand over your whole block of gold. So instead, what you can do is you put the gold in a locked box, kind of looking like this, and the jeweler has to work on the box through the gloves. And the jeweler never gets to open the box. So the jeweler doesn't get the key to the box. That's kind of a key point here, is that they don't get the key. So the jeweler works on it. They make the jewelry. The rest of the gold is left in the box, so that you know they didn't take it. And they give it back to you, and then you unlock the box when you get it back. So this is very analogous to what we're doing with your data when we put it in this locked box, which is the encryption, and then it can be worked on by the cloud, for example, and then the cloud can return to you some encrypted results. So that's a fundamental concept of homomorphic encryption. And the way that we actually enable this is some very wonderful and beautiful mathematics. Now, I'm not going to spend too much time talking about the mathematical history of this problem, but just to give you a kind of a timeline so you know a little bit about how things evolve in cryptography. Homomorphic encryption was an open problem for about 30 years until 2009 when Craig Gentry came up with an initial solution. And since then, many, many researchers have contributed to improving and extending this solution and making it more practical, including our group here at Microsoft Research, who's been working on this area for about 5 or 6 years, especially working on building robust applications, especially to kind of genomics and health privacy issues. But if you look at the history of cryptography, so in public key cryptography, these factoring-based systems like RSA were introduced in 1975, elliptic curve cryptography in 1985, pairings was another big area in 2000. And in each case, there was something like at least a 10-year time lag before these kind of new mathematical problems and solutions could be adopted by the industry. And that's just to give people time to think about these problems, start working on them, understand how hard they really are, things like that. And so that's what we're seeing today in our lattice-based cryptography, which underlies these new solutions for homomorphic encryption. They were proposed, roughly 10 years ago, but the community's been doing a lot of work on understanding the security of these problems. And actually, just last week on Thursday and Friday, we hosted a huge homomorphic encryption standardization workshop here at Microsoft Research to bring together the community, both industry and academia and government parties, to kind of agree on standardizing this technology. So that's a very kind of exciting step that will help us to provide the foundations for industry and government and researchers to adopt this technology more broadly, especially in the health and financial industries where there's a lot of kind of inherent privacy issues. So I'm not going to talk too much about, I'm not going to say any more about the mathematics underlying this, but there are some very interesting and hard mathematical problems that have been around for decades, which are hard lattice problems that underlie the kind of the security of these systems. And another nice thing about these new lattice-based systems is that we don't know of any quantum attacks yet. So in this era where we're thinking a lot about post-quantum cryptography, we want to have systems which are robust to an attack by a potential quantum computer. We're very happy to have lattice-based systems where we don't know any new polynomial time quantum attacks. So what I'd like to spend the rest of my time showing you a few demos of this technology kind of working in action, doing these kind of private predictions. So here at Microsoft Research, we've released a library called the SEAL library. There are a lot of articles written in the technological press about it, including a nice picture of a seal. And this has been developed by our group, well, many versions of it over the last 5 or 6 years, but the most recent version was released in November 2015. A recent release, version 2.2, was released in June. And it's freely available, so you can go to our site and download it and play around with it if you want to. So now what I'm going to do is I'm going to show you some demos of this technology working in action. Okay. Okay, can we see the whole thing now? Okay, so this is actually a genomic prediction. So let me just run it. Okay, so I'll run it one more time in just a second. So what we're going to do here is we're going to predict the flowering time of a flower. We're not using human genomic data here because it's harder to get access to do experiments. But we're actually using 200,000 locations on the genome of each flower, so more than 200,000. So this is somewhat representative of real computations you would want to do even on a human genome. It's reasonable to think that you would do computations, when we talk to genomics researchers, could be anywhere from 50,000 locations up to 1 million locations on the human genome. So this is kind of representative of the kind of large-scale data that you have to handle for genomic predictions. And here we're predicting the flowering time for a flower. The average is like 37.2 days. And so what's happened is that this genomic information for the flower has been encrypted and uploaded to the cloud. So what you're seeing here is a live service running in Azure, including the communication time. So when I click Next, it's going to start doing the computation of predicting the flowering time. And you can see it's usually somewhere between 1 and 2 seconds, depending on the communication time. It's predicted that the flowering time is 29.1 days. So what happened was that information was sent up to the cloud, the prediction was done, the encrypted result was sent back, and then it was decrypted locally. So that's what you just saw. And one of the things to keep in mind is that the performance of our homomorphic encryption algorithms depends very much on, it most heavily depends on the depth of the circuit. So the more complicated the function, the worse the parameters are and the worse our performance. So what you see here is even on kind of a large amount of data, if the model itself, in this case, was a linear model, the model is very kind of low depth, then you'll see extremely good efficiency. So the next model that I want to show you, this is a really kind of an interesting example of melding or merging machine learning research with cryptography research. And you'll see a little bit more about this in our next talk from Rich Caruana. So this was a model that was trained by Ron and Rich for doing pneumonia risk prediction. And here the idea is that a patient could come into the hospital and they have pneumonia. And you want to decide, okay, wait, what should we do with this person? This could be very dangerous. This could be life-threatening. Should they be admitted to the hospital? Or, there's a lot of risks of infection and stuff from being in the hospital, so is it better to send them home and have them have chicken soup? So this is kind of a mortality risk predictor. And this is a model that was built based on 46 characteristics. So if you look down in this bottom left corner, you can see there's lots of different characteristics here. Age, I'm not sure if you can see it very well. Diabetes, asthma, chronic liver disease, all these different characteristics down in the bottom. So there are kind of 46 different characteristics. And what they did was to train a model which has actually degree 4. And it's an example of these intelligible models. So these models are no longer linear, not like the previous demo. But what you're seeing here is degree 4 models, and there's kind of 46 polynomials of degree 4, which have to be evaluated. So when I press next, you'll see it being sent up to the cloud, and it's going to do the prediction. And it's going to return the result, which is kind of the mortality likelihood from having pneumonia. So this result was returned, and if you're kind of more over in the green area, then you're a pretty good candidate for going home and having chicken soup. And the interesting thing is here, in that time that you saw, those 8 seconds, what you really saw was that we had done the prediction for more than 4,000 different patients. So each one of these is kind of a different, you see the slider jumping around there. Each one of those is a prediction for a different patient. So we batched a lot of requests all together. So that was kind of a degree 4 model. So what I wanted to show you was kind of our most complicated and kind of impressive prediction task that we can do today already pretty efficiently. There are lots of other models we can do as well, but this is one that we show as an example of this is called crypto nets. So it's actually a neural net prediction that's happening. If you see down in the left-hand corner, you see these handwritten digits. And the handwritten digits are, each one is a little image in itself. And each image will be encrypted and sent up to the cloud. And in the cloud, the computation that's being done is a prediction of what digit is this, what handwritten digit is this. So this is kind of a simple example of image processing. So it's trying to understand this image and give back a prediction of what number is it. And so when the predictions come back, what you'll see is our confidence level that we have actually correctly predicted a certain digit. And again, this was kind of a combination of the machine learning research expertise coming from Ronnie and the cryptography building blocks that we're able to achieve. So we're able to slightly alter the underlying neural net model, the activation function actually, to make this a more efficient process. And as you can see, this was a big surprise to the community that we could actually do deep learning on encrypted data. So this is an example of neural nets running on encrypted data. And so the size of the digit here indicates the confidence of the prediction. And again, in that time that you saw that it took more than 80 seconds is because the model is something that's a lot deeper than the other ones that I showed you. But you can see we did 4,000 predictions in that time. So I'm pretty much out of time, but this was kind of the key thing that I wanted to show you were these predictions running live in Azure on real data to do this kind of tasks and doing them privately. So I think that it was a big surprise to the community that we can already do things like deep learning on encrypted data. And we continue to push this forward, working on the training stage and other things. So I think I'll stop at this point. Thanks. Question?
So I was wondering the accuracy. Yeah, so I was wondering for the accuracy, when you train on encrypted data, then is there any impact? Is the accuracy essentially the same that's obtained if you train on unencrypted data?
Yeah, so there's two different things you can do. One would not affect the accuracy at all. That is, if you train on encrypted data and you use exactly the same training model that you use on the unencrypted data, then the result will be the same. There will be no difference. However, one of the things when I'm talking about the kind of new research directions, sometimes we can slightly alter the model. So in this case, slightly altering the activation function. And then that's part of kind of ongoing research from both machine learning community and ourselves as to how these kinds of changes affect the accuracy of the model. So there can be very small differences in accuracy, and we can even just study that on the unencrypted data. Like, here's all the unencrypted data. Let's see if we change our model a little bit, how much it's going to change the accuracy. And then we can run that model on the encrypted data, and then there's no change between the accuracy.
Thanks for the talk. It's very impressive. You've got homomorphic encryption running at the speeds you're reporting. Nonetheless, I'm curious, do you have a sense of what the performance ratio, what the performance loss is when you're going through homomorphic encryption? I mean, you're giving us absolute numbers, but if you were just to run that as a straight computation, is it factor of 100, factor of 1,000?
Yeah, I can give you a good idea of that. So when we started working in this area around 2011, the initial solutions reported a loss of something like 13 orders of magnitude, so like 10 to the 13 worse. And so what we've been very proud of is in our group, the techniques that we've introduced have allowed us to bring it down to about 6 orders of magnitude worse. So you're still talking about something that's taking you, whatever, if it took a microsecond, now it's taking a second. So this isn't good in general. There's going to be applications that are very, very latency sensitive, and there will probably not tolerate, at least immediately, that level of slowdown. But what we found is that for most tasks, which are, first of all, statistical, when we see what's actually done, in the industry on data, statistical tasks are very, very simple for us to handle. And so the performance that we observe could be perfectly reasonable. And then there's other tasks which are going to be maybe like a training task, which is significantly harder, where our slowdown is considerable, but yet it could tolerate, if you're training a model offline, we could end up achieving performance which is tolerable anyway, even with 6 orders of magnitude slowdown. So it definitely doesn't come without a cost.
Okay, thank you.
We'll have to switch to the next speaker, so let's thank Christine again. So our next speaker is Rich Caruana. Rich is a senior researcher in MSR, a well-known figure in the machine learning community. Many contributions, including this idea of transfer learning, for example. And today he's going to talk about another contribution he made about intelligible models. And this is the kind of models you want to use usually on tasks where you actually care about privacy and this kind of things.
Thanks, Randy. So I'm going to talk about the importance of transparent models in critical applications such as healthcare. And the way this ended up in this session and connected with this work is Randy and I have known each other for many years. I've been doing this work for 5, 6, 7 years. Randy started doing this cryptographic work. And at some point he said, I think there's a chance that the kind of models that you're training to be transparent might actually be useful for us in the homomorphic encryption world. So that's how the connection was made. It's all Randy's fault. And one thing led to another, and now they have this cool demo using this kind of model. But I'm going to start off talking about the importance of the transparent models and how I got into this. And only at the end will I tie it back to the homomorphic encryption. Okay, so let me start. Maybe you've got data for 1 million patients. You've got all the right clinical features. You train a state-of-the-art model. You get an ROC that's unbelievable, 0.95. So you've trained this neural net, perhaps. And now the question is it actually safe to go ahead and use this kind of model on real patients? Is having high accuracy on test data sort of enough to trust the model? Well, all you've really got at this point is some sort of black box that maybe you don't understand the insides of. And it's got high ROC on test data, but that's all you know. And it's going to turn out there are risks of using this kind of model, even if it looks like it's a high flyer. So let me tell you how I first discovered these risks. Back when I was a grad student at CMU in the mid-90s, was working on this pneumonia project. And our goal was to decide if you were low risk or high risk, just as in the demo. So we, low risk, go home, chicken soup, antibiotics, call us in a few days if you're not feeling better. High risk, though, 10% or more of the patients with pneumonia back then died from their pneumonia. You definitely need to be in the hospital if you're high risk. One of our goals was to compare various machine learning methods that were available at the time to see which of them might be best at predicting risk of patients. And I got kind of lucky. The transfer neural nets that I was developing at the time turned out to be the most accurate model that any of us could train on the data. So that was great. I kind of won the competition. And then the question arose, was it safe for us to consider using these on real patients? And I said, no, we should not use the black box neural net on real patients. And instead, we went to the trusted method that everybody uses, logistic regression, when we started talking about real patients. So why did we do that? Why did we intentionally not use the most accurate model? A friend who was training a rule-based system at the time on the same data learned the rule that if you have a history of asthma, it lowers your chance of dying from pneumonia. Okay, so you don't have to have a lot of medical experience to question whether that makes sense. We asked the doctors, and the doctors said, it's probably a true pattern in the data. We consider asthma a very serious risk for pneumonia patients. So we give them really good care. And what you're telling us is that care is so effective that actually they have less chance of dying, compared to the rest of the population. And the story is even more complicated than this. People who have a history of asthma pay attention to how well they're breathing. They probably notice pneumonia symptoms earlier. They already have a doctor. They call the doctor right away. They get an appointment right away because the doctor takes it seriously. The doctor treats them right away, treats them very well. So they're actually like noticing the symptoms early, they're getting to care faster, and they're getting really good care when they get there. And those are all the magic things if you have an infection like pneumonia. So it's not a surprise that, in fact, the asthmatic patients who now have pneumonia have a better chance of surviving. Now, we assume if a rule-based learning system running on the data learned this pattern, then the neural net probably learned it as well. So this kind of problem is sitting in the neural net. And we're thinking of using these models to try to decide who we should admit or not admit to the hospital. Right? So you can see that this could be dangerous for asthmatics. Right? It would think that they're low risk, that they maybe don't need hospitalization, the exact opposite of the care that they've been getting, which makes them lower risk. So this would be a bad thing potentially for asthmatics. And I said, you know, we're not going to use the model not because of the asthma problem. Now that you tell me about the asthma problem, I'm a smart guy. I can probably fix the neural net and make this problem go away. I said, what terrifies me is what else the neural net might have learned that's similarly wrong, but the rule-based system didn't learn it, so I don't know that I have this other problem that I need to go fix. And I said, that's why we won't use a black box model in these patients. So the key to discovering this asthma thing was that some transparent, intelligible model learned something, and we just sort of looked at that model, and it's like, wow, that looks really questionable. We should investigate that further. Okay. So just lessons before we go on to what we're doing about this. It's always going to be risky to use data for purposes for which it was not collected. And that's the world we find ourselves in. Data is easy to collect. We have tons of data now. The data was not collected for whatever you're probably going to do with it. And it turns out because of that, there are going to be landmines in the data. And I'll show you some of those landmines beyond this asthma problem. Note, by the way, we can't have the right data for asthma. It's not ethical to send half of our asthmatics home to see what happens to them if we don't put them in the hospital and give them good care. So we can't even have the right data that we want in many of these settings. It's much too difficult, in my opinion, to try. You might just say, oh, well, you should have recognized this problem in the data. Data is complicated, so we're not going to do that. We're going to set a lower bar, and instead we're just going to try to make a model that we train on the data be as interpretable as possible. So that's our goal. And we think in healthcare, it's just often going to be critical that you have this sort of intelligibility. And I'll mention at the end if I have some time, it turns out it's exactly the same story if you're worried about things like race bias, gender bias, socioeconomic bias. It turns out it's exactly the same story as the asthma problem. All right, so let's jump in. All we would need now would be an accurate model, you know, that's transparent, and then we're there. So unfortunately, we have this problem. Our most accurate learning methods, unfortunately, tend to be the least intelligible. And our most intelligible learning methods tend to be the least accurate on many data sets. So we have this sort of well-known trade-off. And what we're looking for is something here in the cloud, which is, you know, both high accuracy and high intelligibility. And to our surprise, we've made some progress for certain kinds of problems on developing a method that's up in this corner. Okay, we didn't really invent the method. Statisticians are very smart. They invented it in the late 80s. It's called generalized additive models. Let me tell you about it. You've got simple models, just linear things, you know, weight times a feature plus a weight times a feature. Then you got full complexity things here, which are just some complex function of all the features. Fortunately, there's a space in between. This is an additive model. It's a function of a single feature plus a function of a single feature. So it's an additive sum of functions, which can be complex multimodal functions, but they're only functions of individual features. So this is a sort of generalization of this. Instead of just a weight times a feature, it's a function of a feature. Turns out this is a very interesting class of functions. And I'll show you an example of that. And then there's a generalization of this. This sum is the sum of all these functions of individual features. And this sum is the sum of all these functions of pairs of features, sum of all the triples of features. So we can now do pairwise interactions, three-way interactions. What we're going to do is restrict ourselves to just shape functions of individual features and some functions of a few pairwise interactions. And in fact, today all I'll talk about is this. I'm not going to talk about the pairwise interactions. Okay. As I said, statisticians invented this. It's called generalized additive models. And there's some wonderful literature that was done on it. This is considered sort of a classic method now. There's almost not that much research being done on it anymore. What we've done, what we've brought to the table is modern machine learning and computer horsepower. So we're going to do these models in a way that statisticians never dreamed of doing it. And in the process of doing that, we're going to focus on two things. Make them as accurate as possible and keep the transparency, the intelligibility of the model. So that's our goal. Okay, I'm going to skip all the details of how we do that, so I don't want to bore you with papers worth of detail. I'm going to just jump to the model here. So this is a term in our model. This is the Pneumonia data set. There are 46 features in this data set, as Kristen showed you at the bottom of the demo. This is one of the features. This is age. And we're going to spend 3 or 4 minutes going over this graph so you really understand it. So remember, there are 46 graphs just like this. This is just what it's learned for age. This is age across the bottom here. All the people in the study were adults, so they're age 18 to a few people over 100. This is a density at the bottom, so you can see most patients are sort of between 60 and 90, as you might expect. So let me tell you how to read this model. So this is a risk score. These are the numbers that Kristen showed in the demo. That was the sum that the homomorphic encryption model was making a prediction. These are these risk scores. And the way it works is if you, say, have a risk of 1 added to your score, it kind of doubles your chance of death. So that would be a bad thing. And if you have something like a -1 added to your score, that would be great. It kind of cuts your chance of dying in half. And on this graph, let's see, patients who are about 70 have a 0 added to their score. That means being 70 neither increases nor decreases your chance of dying. Okay, so the background rate is 10%. If we now take your age into account, it turns out your chance of dying is still 10%. Until we look at the other 45 features and see if that raises or lowers your risk. So the way you use this is you go to each graph, you find your age or your blood pressure, partial pressure of oxygen in your blood. You look at the graph, you find where you are. You read off this vertical number, you write the number down. Do that for all 46 graphs. Add up all those numbers. 1/1, e to the -x, you got a probability. Okay, so this is how we get risk scores. And again, being down is good. So let's see what the model has learned. Well, let's see. It's good to be young. So being young, apparently, young is like anything under 50. So remember, the model doesn't know anything about young. It doesn't know what age is. It's just learning this from the data. But apparently, it thinks that basically anybody under 50 is young as far as pneumonia is concerned. So that's kind of nice. And then risk slowly rises as you go past 50 to, say, mid-60s. Okay, so that's not too bad. So that's comforting for some of us. And then risk seems to jump fairly dramatically at about 65, 66, 67, 68. This would have been retirement age in the mid-90s. So the bad news is that somehow retiring is bad for you, which is unfortunate. Now, I guess a lot of things happen at retirement. You might change your healthcare provider. You might change your insurance company. Your daily activity might change. The haste with which you get to healthcare so that you can make that meeting on Friday might change. So unfortunately, your risk does go up at retirement. And then risk rises fairly dramatically as you get older. And then there's 2 more interesting things, or maybe 3. Risk seems to rise at about 85, 86. Then it's kind of flat. And then it seems the error bars are big here, but risk maybe drops a little bit at this like 100, 101. So let's talk about those. There's nothing in the healthcare code that says you should treat patients who are, say, 86 different from patients who are 84. So we don't have anything like that in the US. We're pretty sure this is purely a social effect, which is especially in the mid-90s. Like today, I think 95 is the new 85, right? But back in the mid-90s, 85, 87, 80, this is considered fairly old. So we think this is a sort of, Grandpa's 86. He's not doing well. He's already had 2 courses of antibiotics. He's very, very sick. Perhaps we should let Grandpa pass. So, sorry. You don't look 86, let me tell you. Yeah. I'm 25. And this effect could be in the doctor's opinion. It could be in the patient's own opinion. It could be in the patient's spouse's opinion, and it could be the patient's children's opinion, right? So this is probably some combined effect of all of these different groups. And somehow there's this round number where we somehow considered people back in the mid-90s who were like 85 and older to be sort of older in a way that maybe we weren't going to treat as aggressively if they were very, very sick. So we think this is something that the model has detected, which is just a social effect. Now, we think this drop at 101 is exactly the same thing. So here, I'll make you feel better. You've made it this far. We're not going to give up on you now. So let's go for it. You know, 102, let's see if we can make 102. So again, we think that this is a social effect. And in fact, I wouldn't believe this, given the error bars, except that we see it in multiple data sets. So we see this sort of round number effect at about 100, 101. So we think it's people who are sort of going for it. So, okay, and then these are fairly small effects, right? We're talking about differences in risk of 0.1 or 0.2. So this like changes your probability from being 11% to 12% or from 11% to 10%. But they're non-trivial differences. Now, you mentioned having good genes. We think that might be part of the explanation for why the risk is so flat at this high age. So, okay, interesting thing about this model. It's just as accurate as the neural net that we trained. And yet we just spent a couple minutes, you know, sort of understanding exactly what this model has learned. We assume the neural net has learned something very similar inside of it, but we don't know how to get to it. We don't know how to understand it. Whereas this model, we can easily understand it. We can find things and we can say, oh, we need to look at this. We need to examine this. It tells us here we'd love to have a new variable probably, which is retirement, because not everybody retires at these ages. So we'd love to have another variable added to the data set if we could. We probably want to tell doctors, stop treating patients who are 86 and 87 differently than those who are 84, because there's an effect here that probably isn't needed. And then this is interesting. If we're going to use the model to decide who to admit to the hospital, we don't want the model to think that patients who are 101 are actually less risk than patients who are 99, right? So we don't want that. So we would want to fix the model so that at most risk would continue to go flat or maybe slowly rise up here. So this model is not only something that we can easily, it's not only very accurate, but we can look at it, we can try to understand what it's learned, and then we can also try to fix it. So a doctor could fix this. And it's interesting, if we fix that, our accuracy on the test set will go down. But it should go down because our accuracy on the test set was illusory. The model is actually picking up on a signal that we don't want to use. Now, it's interesting, if we wanted to use this model not to decide who to admit to the hospital, but to decide we're an insurance company and we have to provide money for these people, then this is the right model. Like, we actually do want to know that people who are 101 might live longer, because then we'll have to have more money for their health care for the future. So if we're an insurance provider, this is the right thing the model should do. And it should know that asthmatics have a better chance of living, right? The model should do all those things. But if we're going to use it to decide to admit patients to the hospital, we want to get rid of the asthma effect. We want to make sure it doesn't think asthmatics are lower risk, and therefore doesn't put them in the hospital. And we want to make sure it thinks that people who are 101 are high risk, just like people who are 99. It's interesting. Now that we have this intelligible model, it learned some other things. It learned not only that asthma is good for you, it learned that a history of chest pain was good for you, and it learned that heart disease were good for you. And in fact, the heart disease is a bigger effect than the asthma effect. So, and we assume it's exactly the same mechanism. If you have a history of chest pain or heart disease, you're paying attention to how you feel. You come down with pneumonia, you notice the symptoms earlier, you call a doctor, the doctor takes it very seriously, you get in quickly and you get treatment right away, and ultimately these are all good things for you. So these are other things that we would want to remove from the model. So it's good we didn't deploy that neural net back then, because presumably the neural net learned these terrible things as well. But this model is so transparent that we really could safely deploy this model after fixing it, right? After removing these effects and fixing the age 101 effect. But notice that the model correctness and the data correctness really depends on what we're going to use the model for. For an insurance provider, these are good things to keep in the model. For hospital admission decisions, these are bad things to keep in the model. So the model's neither correct nor incorrect. It depends very much on how you're going to use it. And it's very important that you might think you could just remove these features, train the model, and then all these problems would go away once you know about them. That's not true. Because of correlation, remember, these asthma, heart disease things are in the labels. Those patients actually do live longer. Those things are in the data, and because of correlation with other features, the model will do its best to learn those effects through correlation with other features. And now what will happen is you'll have this effect hidden throughout all these other features in a way you can't detect, and it'll also be, even if you knew it was there, it'd be much harder to fix. So it's actually important to keep the most offending features in the model, and then afterwards, see what was learned on them and try to fix it. Okay. Now, it turns out these things are a good match for homomorphic encryption, so let's briefly talk about that. And then there's just some other issues about using these models where privacy is concerned. So let's first talk about homomorphic encryption. So this is a classic deep net. As you saw, the demo that was using the neural net was the one that ran the longest. And it turns out, at least I'm told, the deeper your model is, the more expensive it is to do this sort of homomorphic encryption. It turns out the kind of model we have, this is our age plot. It's a number from this graph plus a number from this plus. It's the opposite of being deep, right? There's no deep here. This is a function of this, which is a function of this, which is a function of that, all the way down. This thing is just give me a number, plus a number, plus a number, add them all up, right? So this is the opposite of a deep model. And it turns out this is very good for homomorphic encryption. This is our age plot. This is a second-degree polynomial that Rennie and I were able to fit to this data. And it turns out it's not a bad fit for this. Now, they ultimately went to fourth-degree polynomials because for some of the other features, you did need a higher-degree polynomial. But by doing polynomial fits to each of these terms in the model, they're actually able to get something that's very performant from a homomorphic point of view. So the good news, too, is by doing this, they're actually able to get a pretty high-flying model. Now, it turns out it's better than, say, random forest on this data. It's not quite as good as our model, our generalized additive model, because the polynomial fits aren't perfect. But it's actually a pretty good model. So it's a competitive model, and then you're able to do the homomorphic encryption, which is great. So let's talk a little bit, just one slide, about using these models for privacy. So, you know, imagine you're one of 1 million patients who gave your data to the hospital or to some group to train this model, and they train this deep neural net. And your question is, wow, is my data hidden somewhere in the 100 million weights that are in this model? You know, you're afraid your privacy is not being preserved and somehow will leak out of this model. Well, the kind of model we're training looks like this, right? This is our age graph again. And you can kind of look at these graphs. The model is so simple and transparent. You can actually kind of look at the graph and you can be assured, like, you know, maybe you know your age is 80. And you can kind of look at it and you say, well, hopefully I helped that number be just right there. But my data is not going to leak from this graph or from some sum of these graphs. So one of the things that's nice about a model class that's this simple is you can be pretty assured that your personal data can't leak out of it. Whereas when you've got this complex model on the left, you actually don't know if your personal data is somehow encoded there in a way that might leak in the future. Finally, let's just talk about one issue that can arise here. So the beauty of these models is that they're so simple, we can actually read them and understand them and even fix them, fix that sort of thing and add a new feature, stuff like that. If, however, we're using this in a world where we're talking a lot about privacy and encryption, then the model's kind of like this, right? You can do the math, some magic thing comes out of here, some summation gets done, but it is important that a human somehow is able to check these models so that they can fix things that we know are wrong, like the asthma effect, heart disease effect. It's very important that we can fix these things. And if we fully hide the model from everybody, like if we can do fully private homomorphic training of the model on data that's also been encrypted, and if no human ever sees the model, then we have a problem, because transparency is actually necessary to sort of trust the model and be able to repair the model. Okay, I think I won't talk really about bias and transparency. I just want to say that the issues that we're seeing for heart disease, for asthma, these are exactly the same issues that show up with race bias and gender bias. It's very important that you can see the model so you can see how racially or gender biased it is, and then you have a chance of being able to not only see it, but to repair it, just like repairing asthma. So let me jump through. Summary, high accuracy on a test set. Most of us would have thought that this was enough. That can be very, very misleading. Realize as we fix the model, remove the asthma, remove heart disease, remove chest pain, as we fix the model, the accuracy on the test data will go down significantly, and it should. The accuracy was always illusory, and we only knew that once we could see the model. Very important lesson. There are just landmines hidden in almost all real data. In healthcare, you've got to be using something you can see. Correctness really depends on what you're going to do with it. These models are working very well. Deep learning is great, but sometimes you got to understand what's going on inside the black box. And it's kind of nice that these models sort of help us not only with privacy, maybe because they're so simple you can understand what's going on, but they also seem to be a reasonably good match for homomorphic encryption. And I should stop.
So we have some time for a few questions.
Hi, thank you very much for a great talk. You use the word intelligible, interpretable, transparent.
Yeah.
And you kind of waved a little finger at causal. And it seems to be like there's a big jump between those first three words, which I don't know the definition of, and causal, which seems to be the thing you're striving for. So I'm curious if you could talk about
It's a great question, great observation, and I removed the slide on causality just because I didn't have time for it. Why do I use intelligible, transparent, and interpretable? It's because I don't know what they mean either. So I just want to sort of get across this idea that we have a chance of looking at the model, trying to understand. It's not that the model is correct and what it does for age is the right thing. If we move features around, remove features, add features, those terms will all change. The only good thing is we can completely understand how the model makes its predictions. It's a completely white open box. So we can see what it's doing. So that's all I mean by interpretable or intelligible, is that we can at least understand how it's making its predictions. And of course, in a very high dimensional space, 10,000 features, this would get challenging as well. These are not causal models. I think causal modeling would be the ultimate answer to all of these things. If we could do that accurately from observational data, that's what I would be working on. It's just a very hard problem. And whether a causal model could ever learn the sort of subtle things that we're seeing for age and other features from observational samples of data, I don't actually know. Ultimately, causality is what we're all after. We do have a hypothesis that the simplicity of these models means that they sort of detect, let's say, the signature of causal-like things. Like, I'm the one who explained that that jump in the graph at 65, 66, 67 was retirement. It could be something else. I could be wrong. But it did seem to find something, and that something led us to try to figure out what it was. So we're the ones who are doing the sort of causal analysis of what the model has learned. But your observation is exactly right. And this is no more causal than a deep neural net. Yeah.
So you mentioned about this correlated features. You give example 3 features, right? Mm-hmm. You said that if you remove them, you could find probably, some intelligible features. But how could you know that these 3 features are not real features, or they are, until you find other correlated features?
Let's see. So the only thing we claim to be able to do is someone who has some expertise, like a doctor, should be able to look at how the model's making its predictions and should be able to notice things that are like, wow, it thinks asthma is good for you, heart disease is good for you, chest pain is good for you. So we want a doctor to be able to understand that the model is actually, like if you have a patient who has all these other feature values, and then if we suddenly make them asthmatic, their risk goes down. And if we now also give them heart disease, the risk goes down further. And if they have a history of chest pain, the risk goes down even further. And a doctor presumably would say, well, that might be a true statement about the world given how we're practicing healthcare. But given that we want to use the model to decide who to admit to the hospital, that's broken. We should not allow the model to do that. What a doctor might want to do is zero out those terms, which is just, so now the effect doesn't happen that having asthma lowers your risk. Or a doctor might even say, wow, I want all asthmatics and heart disease patients in the hospital, plus 10. So just make their risk go through the roof so that these guys will always get admitted. There's nothing magic about those variables. It's just that presumably a healthcare professional would recognize the model was doing something stupid given our intended use of the model, and they would want to investigate further why it's doing that. There's always a chance asthma really was protective, but they don't believe that. More likely, they're going to recognize, oh, it's a problem in the data that's inappropriate given our intended use, and we just need to fix this problem before releasing the model. Otherwise, we'll put asthmatics and heart disease patients at higher risk. Yeah.
So thanks again, Rich. We have to go to the next talk, but Rich will be around. Thank you, Rich.
I'll be around if anyone wants to talk later.
So last speaker for this session is Jung-Hee Jeon. He was kind enough to come all the way from Seoul for us today. Jeon, he's a mathematician, number theorist, cryptographer, and he'll take us to applications in different fields other than health and genomics that we talked about so far.
Yeah. Thank you for introduction, Ronnie. It's my great honor to give a talk in Microsoft Faculty Summit. Today, I'll introduce some more applications of homomorphic encryptions. Okay, let's start with cars. These days, we have more and more the smarter car. So we have this kind of news. The hackers remotely kill a jeep on the highway with me in it. So that's not that difficult in some sense. So just to turn on the scenario was like this. Turn on the jeep's radio, and then rewrite code embedded in the entertainment system hardware, and issue commands through the internal network to steering, brakes, and the engine. Looks very dangerous. So how to prevent these attacks? Usually these attacks are prevented some security means, but no security mean can guarantee the security of these attacks against those attacks. We have different ones. Stuxnet, maybe most of you are aware of these attacks for SCADA systems. In 2010, the malicious computer worm entered computer system in the uranium enrichment facility in some country. So the network was separate from the internet, but they can enter via, we guess, via USB memory sticks. And then what did it? The computer worms vary the rotational speed of the centrifuges and then destroy them. So that is the worm can control the data. So how to prevent the hacking this kind of CPS, cyber physical systems? Also, it turned out to be very hard to prevent malware injections. It's possible sometimes, but not always completely. So do we have any other means to protect this? Not yet. But we have some tools. We want to suggest some tools for important and small CPS systems. We can use homomorphic encryptions. Okay, so this is a basic. This is basics of CPS systems. Cyber physical system is just control system. That is, here we have a plant. You can consider smart car or drones or SCADA systems too. Plant has a sensor, and then sensor send some information to controller, and the controller compute. Typically it's kind of solving differential equations. And then it outputs some signal command to the actuator. So to secure these systems, we can use some encryptions. And that is, sensing data is encrypted and goes to controllers. And the controller decrypts this one. And then it compute after computations, it encrypts again and sent to the actuator. That's good. But the controller itself is not so secure. That is, malware injection can be done to controller. That is, while controller computing with some plain text, the malware can manipulate this. So simply, using homomorphic encryptions, we can do this. That is, just compute on encrypted data without decrypting. In that case, a malware does not know the message inside the ciphertext, so he cannot control. But still, he can make some errors. But yeah, this cyber physical system has their own protection system. So the usually actuator can detect, has a detection system. So some random noise can be detected. Random change of message can be detected, so it can prevent some those kind of attacks. Okay, you can see more details in this paper. And yes, like this. The smart car, for example, the sensor encrypt the data with homomorphic encryption, send to the controller compute without decrypting, and then send the encrypted command to the actuator. But for those encryption does not, the manipulation need not be random. Yes, I will talk about this. Yes, I will talk about this. Please wait. I mean, okay, so it cannot completely prevent the manipulation. So the ideal one is we add authentication here. So that is, we have homomorphic authenticated encryptions. The controller compute on encrypted data, preserving authenticity too. So we can use this one. So here, the restriction is like this. Currently, we don't have fully homomorphic authenticated encryption. But for any degree, we can do. But it's a little bit, slower than homomorphic encryption too. So for some, we implement this one only linear case. So this is our simulations. So fortunately, we realized that the control system is not so complicated in some cases. For example, in drone cases, not so complicated. So the differential equations can be converted into matrix multiplications here. So the objective here is linear homomorphic authenticated encryption is applied to path tracking controller of a drone for safe autonomous flight. We have 4 cases, simply. The case 1 is not encrypted, not attacked. Case 2, not encrypted, but it's attacked. That is most interesting cases. Case 3 is encrypted, not attacked, and encrypted and attacked. Let's see. Oops. Yeah, here you have a drone. It's okay. It's like a small toy example. It's not encrypted, not attacked. The goal is here. The flying toward the desired destination, helipad. So we controlled very slowly because it's expensive, you know. We cannot destroy this one by. And then. Yeah. Thank you. So it's, it's very. If the attacker can control the drones, it's very dangerous. It can be a weapon, like a missile. And then, if it's encrypted, not attacked, it's safe. Yeah, flying toward the destination as it were. And then, so it's encrypted and attacked. And then since it has an authentication property, so it can detect, and then it can return to some destination, some starting point or some other destination like this. So here we used only linear model for this. So for more complicated model, we need better, more efficient homomorphic authenticated encryption. But here this demo shows it's possible, yeah, with the current hardware. Okay, let's move to homomorphic encryption and machine learning. Let me explain homomorphic encryption again. Here, we have two data. We want to compute on F, on input X and Y. Sorry. Here is like a real world, human world. Here is a cyber world. Previously, when we want to use this computer to compute this one, we need to give the plain text, or we store encrypted data here, but when we compute, we have to decrypt. But with homomorphic encryption, blue is like a encrypted world, actually. The ciphertext can be computed without decrypting. And then when we see the result, it's decrypted with the secret key, decryption key. Then the result is the same with the computation without encryption. So we can think of, we can consider this idea to protect the humans against AIs. So we have this kind of articles. We have some fears on AI and robots. And so how to beat AIs? One possible consideration could be we do not provide data to AIs. So can we protect against dangerous AIs with homomorphic encryptions? Not yet. Still not yet. It's too difficult. But we have some idea toward safer AIs and robots. That is, a control system, the protecting CPS can be one tool, and another tool is to do not provide data to AIs. That is, we just provide only encrypted data. That is, let's consider this concept of perfect servant. What is perfect servant? It does what we want it, but without ever seeing my secret private data. Okay, so what does it mean? We can train AI with encrypted data. That is, store data in public cloud after encrypted, and then machine learning takes encrypted training data as input. It outputs an encrypted model. As in the slide of Kristen's slide, the homomorphic encryption can do all the computation the computer can do. It cannot do what human can do, but it can follow all the computations if the machine can do. So the machine, we can do machine learning on encrypted data, theoretically. Okay, this is the framework outline. That is raw data in homomorphic machine learning. Raw data is pre-processed via homomorphic encryptions to encrypt. This red one's ciphertext. And then in the training phase, we take these encrypted data as input, and then we output encrypted model. And this encrypted model is applied to encrypted data to get encrypted prediction. That is the model we are working on. So we have one example, credit scores. So it's a very practical example. the credit score, it can become more accurate when using data from multiple institutions. For example, we can use loan data from banks, and we can use phone bill and credit card payment and utility bills. Then we use more data from multiple institutions. We have more accurate data, but due to privacy laws, merging database from different institutions or companies is usually prohibited. It's not possible. And then we can run machine learning on encrypted credit scores. Here, the training phase on encrypted data is kind of research problem. So you can find a paper by Christine 5 years ago, but still we are working on this. But for prediction phase, it's a little bit faster. And we have alternate ways. It's like this, okay? The same slide. We can use loan and bills encrypt with homomorphic encryptions, and then training and prediction. We have another tools. For simple predictions, we have a functional encryption. That is, what is functional encryption? In homomorphic encryptions, again, when we have encryption of M1 and Mn, we can compute encryption of F of M1 and M2 Mn for any function F. But in functional encryption, with the same input, we can compute F of M1 and Mn in plain text form when we are given F. But still, we should have some secret key related to this F. That is one application of functional encryption is like this. When we are given two encrypted biometrics, like M1 and M2, if we want to check whether they are the same, we can use just hash functions. But in biometrics, we have some noise for input, so we need to check if it's similar to, M1 is similar to M2. So it can be done with functional encryption when given a secret key for similarity, some specific secret key. Okay, so in machine learning, if the prediction phase is only inner product encryption, that is for linear model, we can use functional encryptions. That is, input is like weight, and then private information is these vectors. So the linear model for prediction phase output A dot X, inner product of A and X. Then we can use inner product encryption. Given A and encryption of X, we can compute Fx when we have the secret on A, that is this secret. This secret can be secret too. The weight can be secret too. Okay. And then we have also some schemes still secure in quantum error in this case. And then it's fairly efficient. Okay, so we can compare those analytics with other means like differential privacy or de-anonymizing. So I think if we have the data is more sensitive of privacy, we'd better use homomorphic analytics, even though it's not so efficient in some cases. But as Christine mentioned, it can be efficient for specific application, especially if we batch some cases. And then if the complexity of an analytic function is complicated, homomorphic encryption is not so good for this. But we can improve the efficiency, but until that, other means would be better for practical purpose. If I have time, let me conclude with introducing what homomorphic encryption is. That is, it's not so monstrous things. Actually, this is easier than RSA in some case. Let me spend 2 or 3 minutes explain what real homomorphic encryption is. it's a symmetric setting. That is, we consider two primes, P and Q, and then operation key. It's public, it's P times Q. Encryption is very easy. Just take M modulo P and M modulo Q. Here, M is an integer between 0 and PQ. Easy. And these, we know the decryption is easy to use Chinese remainder theorem to recover M from this one and this one. It's quadratic complexity. We know the modulo P, modulo reduction is homomorphic with respect to addition and even multiplication. That is, M1 modulo P, M2 modulo P, if we add, it's the same with M1 plus M2 modulo P. It has homomorphic property. Only problem, this scheme was proposed in 1978. Only problem is it's not secure. Okay, it contains all the functionality and very efficient. What does it mean? If we have one plain text and ciphertext, and the difference is a multiple of P. So if you have several pairs of plain text and ciphertext, you can take, we can take GCD to compute P. So one great idea is to use noisy plain text. That is, instead of using all the bits as a plain text, we add some noise here, and then we have very lots of, we fill with zeros for lots of positions. Then it works. Thank you for attention.
Thank you very much. We have time for a couple of questions. I want to take the first question. In your demonstrations in the cyber physical space, is the technology ready for application like self-driving cars where you have high throughput, low latency kind of setting, or is there still some barriers in front of us?
Yes, we need to improve more for using more complicated real-time system like a smart car. That's very interesting application, but we need to develop more.
Just a second, wait for the mic.
Thanks. I also have a question on the smart car example. So you assume that the controller sends the encrypted data to the actuator who decrypts and then executes the commands. So then does the actuator then needs to have some piece of code that execute the decryption? And if that's the case, is it easier to just hack the actuator than the controller?
Yes. This is security model. I should have mentioned the security model. In this security model, we assume the engine or the plant itself is secure. So I discussed this one with the expert in this area, control systems. If we can inject some malware or some, we can contact the engine itself, we have more ways, to destroy them. So it's reasonable to assume the engine is safe, and then but the controller can be a smartphone or some other CPU remotely. So yeah.
We have time for one more question.
Thank you. When it comes to smart cars, do you think there should be some level of minimum security requirements before they're allowed to be on the roads?
Security requirement when we're using homomorphic encryptions? Or?
Yes.
I do not know. Well, for smart cars, I heard that they have lots of the control system in there. So first, we can try to apply this technique to engine, I mean, the brakes or the accelerator. But for security of the smart car, we need to discuss this one with the expert in cars, I think, yes. It's just the initial step, yeah.
There's one more question over there.
It's actually just a small comment. You mentioned two different approaches for obtaining private machine learning techniques, right? Differential privacy and homomorphic encryption. We also have multi-party computations.
Oh, yeah. Sorry, I'm sorry. Yeah, sometimes, yeah. So actually, the homomorphic multi-party computation can play similar role with homomorphic encryptions. The difference is like interactions. Yes, I'm sorry. Yeah.
Okay, let's thanks, Jung-hee, again.
Yeah. Thank you very much.
And thank you to all the speakers that presented here today, and thank you all of you for coming and joining us.